All right, so here's a summary of what we've calculated so far and the stresses and the distributions. So each of these vertical lines will represent the cut face. I'll start with my normal stress at A, or my normal stress due to the normal force. My normal force was here. My moment, tension at the top, compression at the bottom, and my shear force. And this is where point A is on the cross section or on the face of the cut. And in fact, this time I'm going to be even more specific about point A. I'm going to use a square to represent it. And I will just go ahead and recap the numbers. And so now if I want to figure out the state of stress at point A, I would have the normal stresses acting at A can be added together. So my total normal stress at A is equal to the normal stress due to the normal force plus the normal stress due to the bending moment. And in this case, this is 0.533 MPa causing tension or acting away from the face of A, this green cut face, plus 6.40 MPa acting or causing compression on that green cut face. And so when I add this up, it's going to be a difference, and the result is going to be 5.87 megapascals acting or causing compression on that green face of A. The shear stress, there's only one shear stress here, and so the shear stress at A it's only due to the shear force is 0.256 MPa, and on the green face here it's acting upwards. So when I draw my representative volume element at A, it's like, again, I'm taking this cut section, so here was my beam and I cut it right here. And point A, right here, there was this little green spot that I had for point A, and this is point A right here. So that if I were to zoom in on this thing, what I would see on the cut face, which is represented by the green side, and here this cut face is experiencing a total normal stress of 5.87 megapascals going into the face, and the shear stress is 0.256 acting upwards parallel to the face or the cut. And by equilibrium, this differential volume element or representative volume element must be in equilibrium because my entire structure is in equilibrium. Here, if I think of the area that it's acting on as a unit area, then this side must also have 5.87 MPa. And by equilibrium, or some of the forces in the vertical, the resultant force of here must be equal and opposite here. And then by sum of moments about point A, I can't have this differential volume element rotating in space. So here by equilibrium I would have a shear and shear here, and each of these would have 0.256 MPa. And no one says you have to write the equilibrium equations. What you have to remember though with shear stress is that arrows meet in the corners, okay? And you know, this 5.87 MPa. If you write negative 5.87 with the arrow causing compression right here, you actually mean the opposite. So all you need to do is put direction and magnitude for all these stress states. And that's how we draw the representative volume element. Last but not least, I'll just show this to you real fast in 3D. If you were to actually look at the 3D element, let's see if I can draw this. So the green represents, again, the cut. And this surface A is actually right here. This is that side view right here. And my stresses, and you can't see it in a 3D picture, but on the other side, on the side you can't see in blue, there would be a shear stress here and the shear stresses here. All right, I hope this video was useful in giving you a sense of how to attack or how to solve combined loading problems. Let me know if you have any questions. Keep on balling. Structure free.